Hello everyone, welcome to this presentation on our mechanism sessional project, the railway ladder system. I am Mauryavardhan Singh and along with my teammates Mayank Nagar, Krityapriya Bhaumik and Shubham Kumar Mandal. We are excited to walk you through our complete design, synthesis and simulation process carried out under the course Mechanism Sessional at Indian Institute of Technology, Kharagpur. Here is the complete project roadmap for today's presentation. We will start with the objective, move into the theory and go through the synthesis, followed by simulation and finally discuss our areas of innovation. Let's begin. Our objective in this project was simple yet impactful: to design, synthesize and simulate a railway ladder system that allows passengers to safely board train coaches from platforms of varying heights. To achieve this, we have followed a structured approach. Firstly, we assumed a suitable distance between the platform and the train. Then, we estimated the basic dimensions of the stairs. Next, we decided the open and closed configurations of the mechanism. Using graphical synthesis, we determined link lengths for the 4-bar mechanism. Finally, we designed and simulated the complete model in Fusion 360. To ensure continuous motion of our 4-hour linkage, we applied Grashoff's criterion. According to Grashoff's law, the sum of the shortest and longest link lengths must be less than the sum of the remaining two. For our mechanism, the shortest link length is 240 mm, the longest link length is 520 mm, and the sum of the remaining sides is 780 mm. So, as we can see, the sum of the longest and the shortest lengths is coming out to be less than the sum of remaining sides. This confirms that our mechanism satisfies Grashoff's condition and ensures continuous relative motion. So now I will explain the synthesis part using MATLAB. So this is the basic overview of the code that we have written in MATLAB. Now I will go to MATLAB and explain the working. This is our MATLAB script where L1, L2, L3 and L4 have been predefined. We vary only theta 2 and calculate theta 3 and theta 4 using the Newton-Raphson iterative method. First, I will set theta 2 as 40 degrees and then run the code. This corresponds to the train being at the station with the ladder in fully open condition. The difference between theta 3 and theta 4 comes out to be 80 degrees, which matches the wide open angle of the ladder arms. For velocity analysis, omega 2 was given as 10 radian per second and we obtained the corresponding values of omega 3 and omega 4 as we can see. For acceleration analysis, alpha 2 was set to 4 radian per second square and we calculated alpha 3, alpha 4 and the acceleration of joint C as you can see. Now I will change theta 2 to 14 degrees. And run the code again. Now as you can see, the theta 3 and theta 4 values change accordingly and the difference reduces to around 14 degrees, indicating that ladder is nearly closed. The velocity and acceleration values also update accordingly and that represents the folding motion of the mechanism as you can see. So this was the code. Now I'll move to the 2D simulation part that we have done using the motion gen. Here you can see the 2D mechanism animation showing the opening and closing of the ladder. Motion gen also allowed us to generate joint velocity graphs, acceleration graphs and displacement plots, all of which validate the smooth continuous functioning of our design mechanism. The velocity graph remains smooth and continuous, confirming no jerks or singularities. The acceleration response also stays within acceptable limits, and the displacement curve shows proper closing motion as expected. Now I will move to the Fusion 360 CAD model simulation. Now my teammate Krityapriya Bhaumik will take over from here and guide us to the CAD model.
Yeah. So I am Krityapriya Bhaumik. I will be taking you through the CAD model and the simulation part that I have built in Fusion 360. As you can see here, this is the isometric view of what I have built. I have tried to simulate the real life scenario and have built the part of the coach as well as the ladders, and then this cubert that you can see here is the platform. So now let me remove one of these coach parts so that I can show you properly how the ladder works. So let's go to the side view. Now as from the side view, as you can see, this is the ladder, and this is the platform, and this is the coach. So now I will show you how the ladder moves, and now this is the open configuration of the ladder. Now I will show you how it will look in the closed configuration. This is the ladder in a closed configuration. As you can see, here the ladder is completely closed and within considerable limits of the coach, so there would not be any space unused. Also, as you can see that the lower part of this ladder is lower step of this ladder is outside, is actually coming below the platform. It is not some error, it is actually have been done due to the variable height of the platforms of Indian Railways. So, and also, yeah, one thing that you can notice here is that although the lower platform might seem very close to the platform, but our mechanism is such that it will never collide with the platform itself. So it's a very clever design that we have come up with. Also, I will also show you the working from an isometric point of view. So as you can see, the working of the ladder is very smooth and within considerable limits. Now this is for the CAD simulation part, and now I will give it to Mauryavardhan Singh again for the rest of the presentation.
So this is the analysis that we have done. This represents the side views and the graphs that we have plotted using Motion Gen. This is the isometric view of the complete staircase assembly. On the left, you can see the folded configuration, and on the right, how system fits inside the train chassis assembly. So this is the short video representation of the model that we have built in Fusion 360. As you can see, it works perfectly. Now we'll come to the design innovations that we have thought about. Firstly, what we can do is use a piezo-based sensor and hard stop materials to detect end positions of the ladder. Secondly, we can introduce a radial gear or shaft key locking mechanism to prevent continuous torque load on the motor. Next, what we can do is we can integrate a proximity sensor to detect platform height and adjust the ladder automatically. Also, we can develop an inclined plane configuration for wheelchair passengers, improving accessibility. Next, what we can do is using interlocks and indicator lighting to restrict deployment and ensure safety during night use. These innovations significantly improve reliability, safety, and inclusivity. We would like to express our sincere gratitude to Professor Anirvan Dasgupta for his invaluable guidance, continuous support, and motivation throughout the project. We also thank our TAs for their technical assistance and timely help. Finally, we appreciate the collaborative environment created by our peers and resources provided by our laboratory. Thank you so much for watching our project walkthrough. If you have any questions, feel free to comment below.